Let the picky chemistry stuff continue. Like I said, you always know when I'm sitting that I'm just basically reading notes to you and trying to explain a little bit. There are no problems in this section on acid-base behavior and chemical structure. Just some picky rules for you to know, basically about how you can look at a compound, compare it to another one in terms of acid strength. When I do the practice problems, the examples should have some pretty good info on what I'm looking for. These are the kind of things that will appear in an occasional true-false question. There will be some big ideas and some other just picky stuff. This isn't short answer stuff. This isn't what I'm most focused on. When you're looking at ice charts and equilibria and calculating pH, this is definitely a minor idea in the chapter. Factors that affect acid strength based on chemical structure. Looking at a molecule, what do you see and what's different between it and another one? First thing is bond polarity. Bond polarity comes from how electronegative something is. So when I'm looking at HF, hydrogen fluoride, hydrofluoric acid, your electrons, fluorine's so greedy, it's so electronegative. The bond is polarized toward fluorine. What this does is it decreases pH of a solution because fluorine's so greedy that hydrogen is pretty much a free proton. Fluorine has taken the electrons, hydrogen's like, oh no. So the pH will decrease. The opposite is true if you have hydrogen with something like sodium, where hydrogen is the more electronegative atom, pulling electrons away from sodium. That sodium now has electrons that it's able to use to accept a proton. So sodium's going to act like a base. It's going to increase pH. It's going to pull hydrogen off water, all that good stuff. Carbon and hydrogen doesn't do anything. If I throw octane in water, it doesn't change the pH. It doesn't even want to mix with anything. The carbon-hydrogen bond is functionally nonpolar and isn't going to change your pH. You're looking at this probably going, well, HF is hydrofluoric acid, so of course it's going to decrease pH. Okay. In these acids, though, with the formula HX, acidic properties are determined by the strengths of the HX bond, the hydrogen to the halogen bond. Because remember, all your binary acids are group 17, so we're looking at those. We'll look at those, I should say. Determining the ability of the acid to donate a proton comes pretty much from the size of the atom. If you think of it, fluorine is very small and can bond tightly. As you go down the group, you're going to have a pretty big increase in size. Chlorine to bromine to iodine, giving a greater distance between the nucleus of that atom and the hydrogen, decreasing, remember shielding effect? Decreasing the pull on the hydrogen. So you're going to lose that hydrogen more easily, making a solution more acidic. Oxyacids, acids to which OH groups and possibly additional oxygen atoms are bound to a central atom. So oxygen is really, really electronegative. But the characteristic of the central atom, so you got to look at the central atom and see what's up with it. I really don't feel like we're going to see too many examples of comparing with metals. OH is going to be more electronegative than a metal. Metals have low 1 values for their electronegativity, and oxygen's over 3. Even when bonded to the hydrogen, you're going to have a greater electronegativity there. So basically, oxygen pulls electrons toward itself and acts just like its hydroxide, making a basic solution. That's a pretty easy answer. Metal hydroxides are basic. Okay, I am not impressed by that statement because I think we already talked about that. If your central atom is a nonmetal, though, where we're looking at those weird chlorines, or sulfur, nitrogen, your nonmetals, I went to answer the question and went, which has higher electronegativity? I don't know. I honestly don't. Your gray area. It's going to change with the electronegativity of the central atom because nonmetals have a variety of electronegativities, higher or lower than oxygen. So basically, as the electronegativity of the central atom increases, the acidity of the substance increases. It pulls electrons away from oxygen, and hydrogen's like, I'm leaving. So the more the central atom is able to pull electrons from oxygen, the more likely it is the hydrogen leaves, making the solution acidic. As the number of electronegative atoms on your central atom increases, the acidity increases because they're all trying to pull electrons and the hydrogen goes, I'm leaving. General rules For oxyacids that have the same number of OH and the same number of oxygen, we already said more electronegative central atom will make the stronger acid. And the more oxygen you've got, the more acidic a solution is. I kind of like that statement, because it makes sense. If you have an electronegative central atom, it's stealing oxygen's electron, so oxygen's going to give up its proton. And the more oxygen you have, the more that happens. Those two statements are related. Carboxylic acids, I bet those are acids. The oxygen on the carbon stabilizes your carbon. And then like any other non-metal with oxygens, they are acidic. They're able to lose the hydrogen on the oxygen group because of resonance stabilization. This was one of the most boring lectures I've done. There was nothing to draw and nothing to say except if you've got an electronegative central atom or a whole bunch of oxygen, the hydrogen runs away. And I kind of want to run away now. I got nothing. Bye.